Hi guys, welcome to the next lesson in acid-base reactivity unit. So today we are going to talk about RICE charts, and RICE is just an acronym that helps us kind of organize some information. So we're going to be putting together some tables. So first, we have learned about writing the K expression, but those K expressions can be used to actually solve for certain things. So let's talk a little bit more about the value of K. So K is a number, a quantitative number that has been experimentally determined. And in our one of our last lessons, we talked about how if K is greater than 1, that means it's product favored. And if K is less than 1, that means it is reactant favored. So here's kind of a table that you can look up. These types of tables are going to be available in reference charts, in appendixes in the back of textbooks. You can Google a K reference table. And so we have like this whole list, and this is only a snippet of a table, but we have a whole list of different substances, different types of acids. And over here, their Ks are listed. And so we notice that kind of up here at the top, we have several that are greater than 1, like 10 to the positive 9th power. That's a really big number. So these are all greater than 1, getting a little smaller, approaching 1, 55, 28.2. And then we start seeing these negative exponents, which means these are numbers that are smaller than 1. And so I want you to notice that this first bit here, these Ks that are greater than 1, these should look familiar to you as being strong acids. Hydroiodic acid, or HI, HBr, HCl, these are all strong acids. So what that means, remember, strong means that it completely dissociates to its ions, or it completely goes to the right. Like HI is always going to completely make H plus and I minus, and there will be no HI remaining. And that's what this K tells us. And we learned that definition of strong acids, but this value here really supports that, because if K is greater than 1, that means it is product favored, or favors going to the right. That's all this term means. Product favored means it favors moving to the right side of the arrow. And since these numbers are much, much greater than 1, that's by definition a strong acid. They want to make all ions and leave none of this stuff left. So that's just a bit of a review and how you can look at a K value. That last little bullet here says we can use those K expressions and these K values that I can look up in a table and something called a RICE chart to solve for some things, because we can actually find practical data from this. And the thing that we're going to focus on solving for, although there are other variables we can solve for, but we are going to focus on solving for the H plus concentration. Remember, brackets around anything just means the concentration of that thing. And then if we know the H plus concentration, we can go back a couple weeks and use that to solve for pH. Okay, so like I said, RICE just is an acronym that stands for R is reaction, which really just means you write the dissociation equation. I stands for initial concentration. This is the concentration before dissociation happens, and I'll explain what that means in just a second when we do an example. C is how the concentration changes. This is represented as a variable, and usually we just use the variable X. And this is where we take into consideration mole ratios. So does the substance dissociate in a 1-to-1 ratio? Does it dissociate in a 2-to-1 ratio? And so we have to make sure we include the value for how it dissociates on the C line. And then E is the equilibrium concentration, meaning how much of the stuff on the left and how much of the stuff on the right are present together when this dissociates. Okay, so let's just go over what this looks like again on a particulate level, meaning what are the atoms actually doing when they dissociate. So a lot of the times we say the anion is A minus, and that can just represent any anion. I could say this is an a fluoride ion. I could say this is a chloride ion. I could say this was cyanide, the ion. So this is just a generic way to represent an ion. And we know to make it an acid, it's got to have an H plus on it. So when I stick these two things together, this just represents a generic acid. So HA just represents a generic acid. So here we have our generic acid HA. If HA is strong means it completely dissociates, or it has a K value that is much, much greater than 1. So when I put this into water, it ionizes to H plus and A minus. And every time I introduce HA into water, it makes H plus and A minus. So this HA comes in, we get H plus and A minus. So when it's all said and done, all we have is H plus and A minus floating around in our beaker. That is what happens when it is strong. There is no HA left together, only H pluses and A minus ions floating around with the water molecules, which I have not shown here. But what if I have something that is weak? I can still represent a weak acid as being HA. And the way you know something's weak when you look at it is it's not on the list of the strongs that we've asked you to memorize. So I can still represent this weak acid as being HA. So let's say I introduce it to water and it ionizes. And I continue introducing HA to water and some of it ionizes, but a lot of it stays stuck together. So we get HAs floating around in here. We have a little bit of H plus and A minuses, but a lot of the HA stays stuck together. So those are the HAs that are stayed stuck together. And then we have a little bit that has ionized or dissociated in this solution. And so all of these things are moving around. And when we get to equilibrium, which means the moving to the right or moving to H plus and A minus is equal to how often, or the rate at which we move back to HA being stuck together. Once we get to equilibrium, say these guys are floating around in the solution and then they get kind of close to each other. Well, I have a positive and negative charge and they're gonna stick together. But when that happens, if this is at equilibrium, one of these that is already stuck together is gonna break apart. So we're always gonna maintain this ratio of HAs that are stuck together to how many H pluses and A minuses are dissociated into ions. So let's say these guys are moving around and they just happen to come close to each other and then they stick together. Well, then something else has to break apart because the ratio has to remain the same. And that ratio, the quantitative number that represents this ratio, that's where the K value comes from. Okay, so here's the first example, and we're just going to dive right in and kind of take a look at this. I'll do two examples. I'll do one written by hand, and then we'll flip through this one as well. So the question says, write a dissociation equation, a K expression, and complete a Rice chart for 0.53 molar hypochlorous acid. So the first thing we got to remember is hypochlorous acid. From our acid naming, we're looking for hypochlorite, which is ClO minus, and then we slap an H on the front of it to make it an acid. So this is what a Rice chart would look like, and I'm going to go through this step by step. So for R, for reaction, HClO is the acid that's described by hypochlorous acid. That dissociates to H plus and ClO minus. And I suppose I should have a two-directional arrow here to show that this is a weak acid because we only use Rice charts for weak acids. Only use Rice charts for weak acids. So this breaks apart to this and to this ion, and it only partially does that. So when I have a solution, I have some HClO left, some H plus, and some ClO minus. Initial concentration. This is always going to be from the question. So it tells me that I have 0.53 molar HClO. And that's what I put here for initial concentration. The initial concentration of this is 0.53 molar. Then if you think about before this thing breaks apart, if this has not broken apart, I do not have any H plus or any ClO. That's why I put a 0 here. So before this thing breaks up, there's none of this. Before you cut up a pizza, you have no slices. So this is the whole thing, and then this is how much there is before or initially. Then we start thinking about this HClO does start to dissociate into ions, and it changes, but we don't necessarily know by how much it changes. But if this breaks apart, we know that the amount of it is decreasing. So I put a negative sign. I'm going to lose some HClO. It's going to turn into something else. So the HCl decreases. So I put a negative. And I use an X because I don't know by how much it decreases. So this is always negative X. When this breaks up, it becomes these two things. It becomes H plus and ClO minus. So since I'm gaining some H plus and I'm gaining some ClO minus, I put a positive sign because those concentrations are increasing. But again, I don't know by how much they're increasing. And so I use an X. Now this X is the same as this X because when this breaks apart, it produces these things. So if one of these break apart, I'm going to get one H plus and one ClO minus. If 10 of these break apart, I'm going to get 10 H pluses and 10 ClO minuses. So for every X amount of HClO that decreases, I get X amount of H plus and X amount of ClO minus. If I had to balance this dissociation equation by putting a coefficient in front of one of these things, that coefficient would carry down to my X. And we'll do an example of that in just a minute. And then the last line is our E line. E stands for equilibrium. How much is left once everything has done its dissociation? For the E line, all you do is you take the I and the C line and you add them together. Think of it like that. So for E under HClO, I have that 0.53 and I add negative X to it, so 0.53 minus X. For the H plus, I started with 0, I add X, so I end up with 0 plus X. And then for ClO minus, I started with 0, I added X amount, and I end up with 0 plus X. That's how you fill in a rice table, and they're all the same. So it's very repetitive. So I'm going to do one more example by handwriting it, and then you guys have some to practice on the Pear Deck slides. So our next example says to write a dissociation equation, a K expression, and fill in a rice chart for 0.21 molar BeOH2. That's beryllium hydroxide. So a dissociation equation. We take our BeOH2. We verify that this is in fact a weak acid. This is a weak base. I know it's weak because it's not strong. That's the way you know something is weak, is if it's not strong. And it's a base because it has OH on it. So since it is weak, two directional arrow, it breaks apart into its ions. So Be2 plus because beryllium is in the second group. And that 2 helps us, gives us a little clue there. And then hydroxide, but there are 2 of them, so I gotta balance this with a 2, and hydroxide is OH minus. So that is the dissociation equation. Check. Then we're gonna write a K expression from that. So I say K, and I go KB, and it equals products, which is Be2 plus, concentration, and this is multiplied, so be careful that you don't try and add it because you see this add here. So Be2 plus and OH minus, and that is raised to their respective powers from their coefficients. So since beryllium has a coefficient of 1, it gets a power of 1. And since hydroxide has a coefficient of 2, it gets a power of 2. And then we put this all over the concentration of the stuff on the left, or the reactants. So it is always products over reactants raised to their respective powers. Okay, so that is the K expression, and I just realized that I forgot to do the K expression on the first example, but I hope you guys can handle that. And then lastly, we're going to complete a Rice chart for this thing. So remember, R stands for reaction. Well, I've already written the reaction. So when I'm setting my workup, I like to always do the reaction, the dissociation reaction equation, and put the K expression out to the side, because then I can put my Rice table underneath and I don't have to rewrite my dissociation equation. So R we've already got. I is initial concentration, and the initial concentration is given to us in the question. So before this thing starts to break apart, I have 0.21 molar of beryllium hydroxide. And then since it has not broken apart into its ions yet, these guys are going to be 0. So the I is initial concentration of whatever this thing was in the question, and then 0 for the ions. C is how does this thing change? So now it starts to dissociate. So when this thing dissociates, it decreases by some amount. So we put a negative sign to show it decreases, and X to show that it decreases by some amount of X. When this thing dissociates, that means it's forming these guys. And so if this goes down by X, this guy is going to increase by X. And it's a 1-to-1 ratio. So for every one of these that dissociates, it is going to produce one of these. For every time this dissociates, it is going to increase the concentration of that hydroxide, but this is a 1-to-2 ratio. So when this dissociates, it's going to produce 2 of these. So I say 2x. So that's just a little bit different than the last one we did, but it's just based on this coefficient. So whatever the coefficient is here when you balance it, carries down to this change line. And then the last part of filling out this Rice table is I take the I and the C and I add them together. So 0.21 plus negative X gives me just 0.21 minus X. Then 0 plus X is just positive X, and 0 plus 2x is just positive 2x. And I've left the zeros out here because mathematically they're not going to affect anything. And that is our Rice chart. So check. So we have all 3 components that we were asked for in this question. So now try a couple on your own on the Pear Deck slides, and then there's a second video that shows you what you can do with this now to actually solve for some information.